for the n variable case, right. So, let us look at an example of this special case scenario. Okay. So, the example involves motion of a free particle. Okay. So, to describe the motion of a free particle, let us define the coordinate vector of the particle. So, q bar which is q1 of t, q2 of t, q3 of t, right, which we say that this is the Cartesian coordinate of a free particle of mass m, right, at time t. Cartesian coordinate of a free particle of mass m at time t. So, then in that case the motion is going to be described using the sum of its kinetic energy and the potential energy, right. So, in that case the kinetic energy of the particle, let me describe it using this abbreviation k dot E, is defined by the function t of q bar dot, which is nothing but half m v square or half m q1 dot square plus q2 dot square plus q3 dot square. So, this is mass times the square of velocity or the kinetic energy. Finally, the potential energy, denoted by the abbreviation P E, we define it to be negative of V of t comma q, right. Let us to begin with, let us say it is described with a positive sign, right. So, and of course, this potential energy is a scalar function. It is a scalar function of a vector, right, because this is an energy. So, it must be a scalar function, and also scalar functions, and also it can describe the forces. The force is described by the gradient of this potential with respect to this coordinate vector. So, this is standard Newtonian mechanics. The gradient of the potential with respect to the position gives us the net force on the particle, right. So, let us continue. Then we describe, so this is the kinetic potential. We also now describe the so called Lagrangian, right. So, what is Lagrangian? So, Lagrangian is the functional. In calculus of variation language, Lagrangian is the functional, it is a function, it is basically the integrand of the functional. It is a function which is described by L of t comma q bar dot, which is also equal to t of q bar dot minus v of t comma q bar, right. So, we see that so the Lagrangian is this following quantity. When we substitute the values of t and v, we see that this is also equal to half m q1 dot square plus q2 dot square plus q3 dot square minus v of t comma q bar. Okay. Now, what is this, in this particular example we will see that the Euler Lagrange equation reduces to the conservation of energy. That is the beautiful result in this example. So, let us look at the Euler Lagrange equation, but before that let me introduce a new concept. So, let us now digress. So, there is a brief digress from our original discussion. Let me now introduce the so called Hamilton's principle, right. Hamilton's principle, right. So, what is Hamilton's principle? Hamilton's principle is nothing but that it is just the physics language of the variational calculus, right. So, let me write down a little bit of trivia about Hamilton's principle. It turns out that Hamilton's principle is also known as the principle of least action, principle of least action, the principle of least action, right. All these words will become very clear as we move along our course discussion. Okay. So, another fact is that when we find the extremals for these example and other similar physical examples, not necessarily the extremals will be either maxima or minima. The extremals could very well be saddle points, right. We are going to describe and distinguish between the different types of extrema later on when we describe the sufficient condition for the extrema, right. So, what I just said is that finding extremal does not guarantee us to find max or min. So, extrema could also be saddle or saddle point, right, not just minima, right. And Hamilton's principle is sometimes more advantageous than just looking at plain Euler Lagrange, because it is more general, it is more general than Euler Lagrange equations, because first of all it is applicable, for multiple coordinate system, right. So, functions of several variables, dependent variables, and it is also more often than not applicable for different coordinates. So, in particular it is also applicable for non-Cartesian coordinates, right. So, that is some of the advantage of using Hamilton's principle. Now, coming back, so what is Hamilton's principle? Hamilton's principle says that, Hamilton's principle says that the path of the motion of the particle from, let us say, q bar of t naught to q bar of t 1, the path of the motion of the particle from q bar of t naught to q bar of t 1 is such that q bar is an extremal, of the form j of q bar is equal to the integral from t 0 to t 1 L of t comma q bar dot dt, right. So, the path of the motion of the particle from point A to point B is such that q bar is an extremal of this particular integral, also known as the action integral, right. So, the Hamilton's principle is nothing but the Euler Lagrange equation stated in the words of physics, right. So, essentially this is the Euler Lagrange equation. Okay. So, moving on, so we are going to, let us go back to the previous slide. So, we are going to find the extremum for the motion of the free particle. We are going to use Hamilton's principle and find the least action or the extremum of the action integral, right. So, what essentially we are doing is we are solving the Euler Lagrange equations. When we are applying Hamilton's principle, essentially we are solving Euler Lagrange equations for the n variable case. So, when we do that, we have the following set of equations. right, and this is for k1 to n. Now, let us now plug in the value of L, right. So, notice that L is half m summation qk dot square plus, well, not plus, but minus of v of t comma q bar, right. The why minus? Because as we increase the coordinate of the particle, physically it is assumed that the potential energy decreases. So, it has an inverse relation. So, L is the Lagrangian, and when we plug, we see that in this first partial qk dot only appears in the first term, that is the kinetic energy. So, this, after plugging in the value of L, we get that this is also equal to m times q k double dot minus the second quantity, which is the partial L partial q k, only appears in V. So, I get that this is also equal to this is also equal to del V del q k for each component, right. So, what we have is well, it becomes a plus because we have a minus here, right. So, this is equal to 0, or I have that m q k double dot is equal to minus del V del q k. And people who have done basic Newtonian mechanics, we see that the derivative of V with respect to q, or the gradient of V with respect to q, gives us the force on each component, right. So, essentially I am saying that, and this particular quantity on the left hand side is nothing but the acceleration of the kth component. Now, I am sure students can easily recognize that this equation is nothing but Newton's second law, that is mass times acceleration is equal to the net force on each component. Okay. So, we have essentially written Newton's second law while solving the Euler Lagrange equation. Okay. So, then the physics follows beautifully in this case. So, suppose now we can look at a special case where our potential is independent of t. Notice that t only appears, the independent variable t only appears in V. So, suppose if the potential also is independent of t, then my Lagrangian will be completely dependent on q bar dot and q. It is independent of the independent variable t, and then we could directly use the Beltrami identity to reduce our Euler Lagrange. So, what I just said is the following. So, further suppose I have that V of t comma q bar is equal to V of q bar, right, which is a potential independent of t, right, and we see that in this case L, my Lagrangian will also be independent of t. So, L is independent of t, right. So, in this case my Euler Lagrange reduces to the Beltrami identity. So, my Beltrami identity becomes H, which is equal to summation q k dot del L del q k dot minus L is equal to a constant, right, where this summation is from 1 to n. Okay. So, we just plug in the values of this function L, and while we do that, we see that my Beltrami identity H of q bar dot reduces to half m q1 dot square plus q2 dot square. This is a 3D space system for one particle plus V of q bar, and of course, this is equal to constant via the condition of the Beltrami identity. Notice that the Beltrami identity has very beautifully resulted into the conservation of energy. So, this statement is nothing but the conservation of energy, which says that the sum of the kinetic plus the potential energy is constant or conserved. Okay. So, let us look at a related example. Let us look at an example of a not really a freely moving particle, but a particle performing a certain motion. So, I call this example as example 2a, namely I am going to look at the motion of a simple pendulum. So, let us say I have a blob of mass m, let us say this is the blob of mass m, and it is hanging by a rope of length L. The rope has almost 0 mass, right, and the blob is under the influence of the gravity, and further the coordinates of the blob are x of t comma y of t, right. So, I want to x of t comma y of t. So, this is my coordinate of the blob. So, we see that in this case the motion of the simple pendulum, in this case my kinetic energy. So, we need to write all the different forms of energy. The kinetic energy in this case will be half m v square. So, half m x dot square plus y dot square, because these are the two different components in 2D. We are talking in 2D, and notice that x1 square plus y1 square is nothing but, if this is my L and this is my phi of t. So, this is nothing but the total area of the arc that is swept. This is nothing but in terms of L and phi, this is going to be L phi dot t whole square, right. So, yeah. So, that is the case here, right. So, how did we get that? Well, we are assuming very small oscillations, right. Well, how did we get that? Let me just briefly mention that. So, if my phi is very small, if I represent x and y by its polar coordinates, I see that x is L sin phi, y is L cos phi, and for phi small, sin phi becomes phi and cos phi becomes 1, and when we plug it in this expression, we get that this is also equal to L square phi dot square, right. Okay. So, this is for small angle of oscillation. Okay. So, then my potential energy of the problem, becomes V is equal to mgh. Notice that h will be this quantity minus the total quantity, which is L. So, this is also equal to mgl minus this quantity, this is L cos phi. So, this is L minus L cos phi. So, this is how much the ball is above the ground, or this is also equal to mgl 1 minus cos phi, right. Okay. Moving on. So, what we have is the following. You see that now we have written both the kinetic and the potential energy. So, now I can write down my action integral. My action integral f of phi is given by the following integral from t0 to t1 of the total kinetic energy minus the total potential energy. I am just writing the Lagrangian from my previous slide, right. So, this is phi times dt. Okay. So, then we see that here this is L of phi comma phi dot. So, there is no explicit appearance of T in this Lagrangian. So, I can very well use Beltrami identity, and my Beltrami identity says that using Beltrami identity, I see that I get half m L square phi dot square plus mg L 1 minus cos phi. So, that is my Beltrami identity, which is the sum of the kinetic energy plus the potential energy will be a constant, or the conservation of energy, right. So, what it says is now that the extremal phi is going to satisfy this conservation of energy. So, the next step involves trying to remove the constants as much as possible. So, we divide throughout by m L square by 2, and we get the following expression, that we have phi dot square plus we have g 2g by L 1 minus cos phi is equal to, let us say, a constant C naught, but again 2g by L is another constant. So, that can also be absorbed on the right hand side. So, we get that phi dot square minus 2g by L cos phi is equal to another constant C1, right. So, now to solve this particular equation, we first differentiate this equation with respect to our parameter, our independent variable t. We see that after we differentiate, let me call this as star, we differentiate star with respect to t, we see that the following solution exists. So, we have this minus 2g by L sin phi times so, we have a cos phi with a minus will give me plus sin phi, and times phi dot is equal to 0, right. So, phi dot appears in both quantities. So, it is taken out common, and further we assume that phi dot is not 0, right. Otherwise, we are going to get a trivial solution, phi is a constant, and that is something we are not after. So, which means that from here we get that the solution reduces to the following equation, 2g by L sin phi, which is equal to 0, right. So, then the next step is, since phi, the oscillation angle is small. So, since phi is very close to 0, small oscillation angle, we can reduce the equation further by saying that sin phi is equal to phi itself, and then in this case the equation reduces to phi double dot plus the constant times phi is equal to 0, and this, the solution to this equation will be a linear combination of sine and cos of a constant. So, I can write down this solution, phi of t is, let us say, in terms of a constant sine of square root g by L times t plus phi naught. So, it is a solution with two unknowns, a and phi naught, and these two unknowns are determined by the boundary conditions, okay. And that is where we can stop our discussion on this example, okay. So, next we look at another example, namely the brachistochrone in 3D, right. Brachistochrone in 3D. Okay. So, again, what is the problem? The problem again is to find the optimal curve in 3D now, so that a bead sliding without friction reaches at the bottom of the curve in the minimum possible time, but this time the curve is in 3D, right. So, the problem is find find the points or the curve of fastest descent between the points x0, y0, z0 and x1, y1, z1, where my z is the height of the curve, and I have two dependent variables y, z. They are functions of x. They are functions of x. Okay. So what I have is the following. So we see that to figure out the solution to the brachistochrone in 3D, we again write down the time functional. So our time functional is t of y comma z. So these are my two dependent variable, comes out to be 1 by square root 2 g. Again, using the same argument that we did for brachistochrone, we spoke for brachistochrone in 2D. We get that this is equal to the total arc length 1 plus y prime square plus z prime square dx divided by square root of z naught minus z, right. Then, well, of course, now we have two dependent variables, and both are dependent on x. So which means that we are going to have two sets of two Euler Lagrange equation, one for y, one for z. So which means we have the following system of equations to solve. So the first system is for y, we see that this integrand is only a function of y prime, right. So which means that our Euler Lagrange equation is simple, relatively simple, which is of this form: y prime divided by square root of 1 plus y prime square plus z prime square, square root of z naught minus z, right. This is set equal to 0. This is the Euler Lagrange with respect to the variable y. The second is the Euler Lagrange with respect to the variable z, and we see that the equation reduces to the following form. Minus 1 plus y prime square plus z prime square divided by 2 times z naught minus z to the power 3 by 2. This is equal to 0. So this is my Euler Lagrange with respect to the variable z. So then we can start solving each of the equations 1 and 2. So from 1 I can directly integrate 1. I see that I get a solution y prime divided by 1 plus y prime square plus z prime square is equal to C1 times square root of z naught minus z, right, where C1 is a constant of integration with respect to x. And let me call this as 1 prime, and then if we are to solve 2 prime, notice that 2 prime is a mess and it is not going to be easy to solve 2 prime, right. But let me call this integral as 1, but we note that that 1 is also independent of x. So we can definitely use Beltrami identity for two variables, right. So what I just said is the following, right. Solving the second equation, solving this equation is a mess. Solving equation 2 is difficult. It's difficult, but we have to note that 1, the original integral is independent of the variable x. The original integral is independent of the variable x. And so, in this case we can write the Beltrami, we can use the Beltrami identity. Okay. So, in this case we have the identity with respect to two variables y prime, z prime. This turns out to be the following form. Minus f is equal to C2. Right. So, now we can directly substitute our small f, that is the integrand. We see the following. We see that this is also equal to square root of 1 plus y prime square plus z prime square divided by square root of z naught minus z minus y prime square divided by, I have just plugged in the expression for small f or the integrand of the functional. We get the following expression, a huge expression which we eventually simplify. This is also equal to the constant C2. So, when we simplify after taking the necessary LCM and common denominator, the simplified version reduces to the following form: 1 by square root of 1 plus y prime square plus z prime square. This is also equal to C2 times square root of z naught minus z. So, let me call this particular relation as 2 prime. So, we have two new sets of equations to solve. One is given by this 1 prime and the other is given by 2 prime. So, for the variables y and for the variable z. So, what we can do immediately, we can divide 1 prime by 2 prime. So, we can divide 1 prime by 2 prime to see that y prime is equal to C1 by C2, right, or I get that y of x is equal to the quantity C1 by C2 times x minus x1 plus y1. So, we get for the variable y, we again get the equation of a straight line. However, it does not contain any z, which means z can take any value from minus infinity to infinity. So, what I am trying to say here is that this new equation is not the equation of a straight line, because there is the variable z as well. So, this is an equation of a plane, parallel to the z axis, right. It could contain z axis, but not necessarily. So, this is vertical or parallel to the z axis, right. And then the further solution can be found by solving 2 prime, and we will see that the further solution will be a cycloid. This equation is nothing but the equation for a cycloid. So, which means combining this solution which is in the box with the motion of the cycloid, we conclude that the brachistochrone in 3D leads to an extremal which is a cycloid in a plane parallel to the z axis, right. So, what I said is the following. So, further 2 prime gives the relation between y and z, which is going to be, once we solve, is going to be a cycloid. And so, the following conclusion can be drawn. The following conclusion can be drawn that the solution to the 3D brachistochrone, the solution to the 3D brachistochrone can be reduced to the solution to the 2D brachistochrone in a vertical plane, right, in a vertical plane or a plane parallel to the z axis. Okay. So, that is what we have.